Okay, hi everybody. My name is Rafał Kurda. I'm from Mobica, and today, as I talked shortly before, I will talk about model performance analysis, and that I will try to convince you that we should go further beyond just accuracy, just the printing confusion matrix, and all of the stuff that we can actually read in the scientific papers, because they are not very well fit into proving that uh, the models will be performing good in the production. So why did I choose this topic, and why it is important, and why it's a problem, and why we should care? So first of all, machine learning is quite a young discipline, and we still do not have a lot of written down good practices that we should follow to evaluate models before we put them into the production and before we show that to clients. Furthermore, researchers are very academic-based creatures. They are focused on performing, research and producing research papers. And paper will accept anything. You can, if you want to get a good research, you can slightly modify the metric, maybe tune up a little bit of the graphs, and you will get a good paper. But it doesn't mean it will be good in production. And furthermore, the metrics that are used in papers were really never focused on production rather than on solving some particular task. On the other hand, ML engineers who are who came into this area from another areas like regular software development, they know very little about statistical techniques. They know very little about confidence, and do not know how to report that, how to be sure that the model that they released is worth trusting. So let's start with some example to make this a little bit more realistic. I found very interesting papers about predicting pneumonia deaths. It's a quite old data set from 90s. It has 13K examples, so it's not a small data set with detailed data, biometric data about the patients, and also with health data. The task is to predict whether the patient will die from the pneumonia or not. And the objective of this challenge, of this task, was to prioritize patients in hospital queues. So hospitals cannot accept everybody, so we want to prioritize patients who have higher probability of dying from pneumonia. So after a few trials, achieved accuracy was extremely high, like 0.85. So it's kind of good for such an suggesting solution. However, it turned out to be a failure. Why? Because after close examination, it turned out that the model learned a lot of strange rules. For example, that a patient with asthma will have a lower risk of dying once being infected with pneumonia, which is definitely not true. So the asthma is an infection of organs that are connected with the whole inflammatory system, and anything wrong there connected with pneumonia will lead to a higher risk of dying. So why does it that it happened that all of the machine learning system models during training learned such a rule? So the problem was in the data set. So so the data set was gathered in the normal hospitals, and any patient that had pneumonia and asthma was immediately, without any hesitation, admitted to hospital ICU, means intensive care unit. So in a data set, those patients had very little probability of dying because they were immediately admitted. There was no delay because and that was a very clear rule. And however, the models didn't get that because there was no data of a patient with asthma and pneumonia who died. So all of the models learned that the risk is low. So how to fix such problems? First of all, we will need to focus on a data set so that the data set is fuller. However, in this scenario, it's not possible to get a bigger data set because no one will allow you to gather, to forcibly put patient in risk of dying into some strange medical procedure just to get a data point for training your model. So given that we have these constraints, we should first redefine the metric, probably to something like should be patient admitted or not, and tell all of the user that this prediction will be given some error. And such a metric that I mentioned should be validated with doctors who have fuller knowledge so that such errors can be fought. These are just examples of fixes. There are probably many more. So the metric actually is a very central part of machine learning. Choosing one is very difficult. And definitely, for example, when we are doing something with classification, we shouldn't just focus on accuracy. If we want to employ it in a business scenario. So business cares about money, time, and public image. And those are the metrics, very vague, but those are the metrics that should be important. So model is even 99% accurate, but the financial losses from this 1% of errors are huge and cost a lot of time. This model will be a crap. So you should develop metrics. Furthermore, the last but not least problem is that a bad metric will inflate expectations. So if you give a model with a notation that it's 99% accurate, but then it epically fails with a lot of financial consequences, it will be very bad for your trust and public image as a software developer. And probably the business that trusted you in developing that will never give you any other option to develop anything for them. And the last thing that's worth mentioning is that even systems with poor accuracy can be good if they can give some suggestions that will give a lot of savings. So even if they, for example, are 10% accurate and render a lot of false positives, if this false positive is about terrorist attack, it's still worth to implement such a system. So as we talk about metrics and which are the beginning, which are the basis of validation, we can talk further about the user experience of the model. So there is a very huge problem with ML user experience because we did a lot of research when developing computers based on the axiom that systems normally work. However, machine learning failures happen by by design. So every ML system will have a failure. So you should basically employ some expert who is able to help you to create a system that's easy to use and those errors of the systems are not very are not very problematic for the user. I do not render bad experience. So the good example of this is autocomplete suggestion system developed by Google in Gmail. When you get a great text with some probably low probability prediction of what you will write, and it never forces you to do anything. You can just accept that. The very bad example is the famous Microsoft Clipper, who actually wasn't a pure ML system, but was based on some rules. The designers thought that it would be very accurate, and it produced pop-ups that were very hard to dismiss, and the user experience was extremely bad in these examples. But let's define it better. So to evaluate, to make sure that the system will be good from your user experience perspective, it's very important to have other properties like high parsimony, so that we can easily describe why the system is failing. For example, we can, in the driving scenarios, we can say that we should be able to, for example, say that the automated vehicle won't be driving when it's raining or snowing. If, on the other hand, we have a vehicle that behaves like some psychopath and who drives for 99% accurately, but even in snowy condition, but randomly crashes your car, that such a system won't be good. So this should be also measured, probably with user experience and by drafting a good metric. And this is a very important part of validating the system. But let's go back to core ML. That's probably most interesting to everybody. So to validate the model, we need to first of all validate that the data is good. So first of all, we need to learn that the data sets are sparse, even big data sets. So first of all, because we will never get data from dangerous situations. So we're trying an automatic vehicle, we won't get a real data of difficult or dangerous behavior. Furthermore, in a higher scale scenarios, we will never be able to test or train the data on a data set that has a similar size to the production data set. So let's say that we would like to verify that Tesla cars are working properly. It's impossible given the real fleet of Tesla, which is 100K cars. It will generate around 200 or 300 petabytes of data, given that it has 8 cameras. It's amazing data set it's amazing big data set that's very difficult to work and validate. So we must sample the data sets that are used for testing and validation. And this sampling is a very difficult thing because it has to be, it's very easy to sample it wrongly, so that we have something called covariance shift. It means it's as shown on this graphic. We can inadvertently sample data sets in different conditions from one and put them into one data set and different into the other. For example, we can sample from these automated fleet vehicles into training data sets that were gathered only during the day, and then test it on a video clips of a car driving only during the night. So definitely, such a system will never we will never be able to train such a system to a high quality. But still, we can cope this by randomly sampling the train altered data set. The more difficult scenario is when we sample the data sets from reality. So let's say we only gather images, we only gather footages of a car driving through the day, and then we let people drive it during the night. It will lead definitely to the failure. So anytime you train a model, you should make sure that the statistical properties are similar to what will happen in the production and operation. When we talk about these data sets and how to gather them, we should also make sure that the data sets are gathered in a fair way. This is very important for making sure that the model will be successful in production. So the fairness matrix sounds as follows: similar individuals or groups should be treated similarly. So it means that if we gather data, for example, on image recognition just from one city or one country, we will never get a data. We'll never get a good experience and good quality in other country that probably has people of different race or different lighting conditions. So when you gather the data, you must make sure that you treat all of the people equally. And with that, we have a lot of problems because it turns out that the data gathered for face recognition or genomic data is highly biased. On the other, also some criminal data records are highly biased, and it's leading to unfair solutions. So you must validate the data sets before training and testing, and you can improve that by using a lot of tools. So first of all, there are tools called facet analysis tools developed by a lot of companies. So those screens are from tools developed by Google that let you compare the distribution of the training and testing data set. With that, you can make sure that you don't have this train and test split. On the other hand, you should try to use what if tool to analyze failures. So after gathering the data, it may be difficult to check if this data was gathered in a biased way. However, the failure analysis can help you connecting the dots. So you can, for example, on the low confidence end, you can see what's there. If you see, for example, in the face recognition, people from the same race and probably from the same region, it may mean that those people are underrepresented in this data set. The other interesting technique is to use counterfactual explanation. So it works in a way that for example, in a credit loan scenario, in mortgage scenario, you get a person who didn't get a loan, and then you check what is the closest neighbor that would get this mortgage, and it may turn out that probably moving to a different city or moving or changing a sex could change that, and that can indicate that this model is biased, especially when this change would be counterfactual, meaning that it would be very, from human perspective, senseless. However, such a faceted analysis is very difficult due to the lattice problem that you will easily hit while validating that. So probably you can check easily the most popular gender metadata like age, gender, country. However, as you try to check what's the model output on some intersections, like some like female from India who are between 60 and 40, and, for example, have the newest Android phone, you may get you may need to search through millions of facets of slices to ascertain that something is wrong. And while the model should be irrespective of this critical metadata, however, the newest research shows that this can be checked with training. So we can we can train a model to detect whether the metadata, like gender and age, can say what will be the outcome, what will be the accuracy of the model. And if we can do that, if we can predict based on metadata what will be the model performance, it's usually very bad, and that should be fixed through analysis of the data set, maybe getting more data set, maybe there's something wrong in the algorithm itself. The other things that's also very important during the analysis, the confidence intervals. So who does that? Probably very few people. I personally been in many projects that never did that. I also personally don't do that very often. So what's that? When you get a testing data set, you sample it from some bigger data set or from the reality of from the production, and then the number of with the probabilistic theory to everything happens with some probability. So if you have, for example, just 1,000 examples in a given data set, and we can say that the error is given a normal distribution, and the reported accuracy of class A is just 0.5, the confidence intervals of this model are between 0.46 and 0.53. So you have around 0.7% of deviation, and it's actually huge. It means that you are not able to distinguish, to say that the model who has 0.53, you cannot say that this model is better from 0.46. And and often I've seen that people were struggling to push the models by 1 or 2%, even in having very few data samples. And they spend a lot of time and money on trying to do that, while it was senseless, because those advancements were mostly overfitting and couldn't be justified from the statistical point of view. This confidence gets kind of closer when we are also get better with accuracy. However, at this 1,000 examples, still you have around 0.04 possible deviation. So there is really no point on spending your energy if you have just 1,000 class examples to push something from 0.9 to 0.91. But you should measure that with your data set and every class. This confidence interval is best visualized also on the ROC curve, and it also should be analyzed on. It should be always plotted. So it kind of looks like that, given that, let's say, we have this. We have around 500 examples, so we can see that it's very big, especially in some locations. It may be problematic. So if you want to be very low on this left side, for example, specificity, you will get extremely high sensitivity variation. And on the other hand, if you want to aim at some sensitivity, you will get very high deviation on the specificity. So when you want to do a ROC curve analysis, always plot this thing. The other important thing to know with confidence intervals, and this example is the K-validation. That's very often used by people to choose the best model. And it is claimed, and many people say that this strategy is best for picking the best model architecture. However, very few people do the confidence analysis while doing K-validation. If the K-validation dataset is very small, then splitting into those default 5 or 10 classes can make this confidence interval very big. So, and the results between classes can be normally are very slow. So, choosing from so doing K-validation and choosing models that have very little difference is also senseless. So let's go to the other example, also with pneumonia, that should visualize other problem that should be also detected. So the task was to detect pneumonia based on X-rays. It also had a lot of examples. And interestingly, the reported accuracy was on internal dataset was 0.7, and on external dataset, that's my fault. It was 0.3, not 0.8. And this is also very unexpected. They used those researchers who did it used the regular ResNet-based architecture. And that's very well researched, and the dataset is also very good. It was quite varied because they had about 40,000 different patients. So why it failed on an external dataset, meaning that in a production? So the reason was that. So the reason was that the X-ray learned how to distinguish actually the hospital wards. It's hospital wards is oddział po polsku. So normally, while doing the X-ray image, the nurse will place some metal coin or some metal sign that should indicate who was the patient, what was his orientation, and maybe when this photo happened. And neural networks managed to learn what was the mean positioning in different wards of that thing. And it turned out that the different wards have different pneumonia probabilities. So in some ward, which was actually treating pneumonia, the probability of getting pneumonia patient was very, very high, like 80%. However, on a different ward that was connected with cardiac diseases, the probability of getting pneumonia patient was 0.1. So the model never learned to distinguish pneumonia. It learned to distinguish wards. And researchers actually got this explanation by using silency maps. So it's also called activation maps. It means that you can see which pixels influence and the prediction from the given images. So to validate your solution, you should use that. You should get some interpretability of how the model is working, what it is looking for to make this prediction. So let's go to the science now of validation connected with adversarial examples. So if we would like to algorithmically prove that given the output, given the input and the network, we will get some output, or given the constrained input. I mean, let's say an example. It is very difficult to prove that if we have a dog on an image and a changing data set and a changing background, it is difficult to prove that the network will always respond that it's a dog. And it is a very important property because it means that you can never get you can never say to your client that you are 100% accurate, that in some scenarios the network will work. It's happening because neural networks are similar to free SAT problems, and it actually proved that it's NP-hard problem. There are a lot of proposed solutions to work with this issue. The most important are the network coverage ideas. So it is claimed that the adversarial examples that we often see happen because the value functions can push unactivated regions of networks to some state that activates the other regions. So to see whether the network is fully tested given a data set, we should see if then all of the networks during the data set were activated. And this is very similar to close coverage known from the regular software development. Okay, this is the slide about this pneumonia. That showed those signs that were and silencing maps that were that were turned to be decisive factor for the model decision. And yep, we are getting to an end because we have just 10 minutes left. So about me, I'm an ML developer with 3 years of experience and 5 ML projects released to the market. I'm working for Mobica, which is quite a big software consulting companies with a few hundred developers, and we are actively looking for new ML developers. So if you're interested, please contact us. I also recently founded an ML-based startup called Slopai, which is aiming at rising alerts when something is going wrong in the company. It's based on NLP. So let's. Do you have any questions about this material?